All right. Hello, everyone, and welcome to the Lab 1 Health session. I'm Davis,
I'm Daphne.
and so we just put together a couple of stuff that would be useful. I think I'm already recording, to be honest.
Uh,
We just put together some stuff that we thought would be useful in Lab 1 and would answer some common questions that we saw in office hours. Okay. So first off, we're gonna go over some stuff from Lab Zero that may be helpful to remember, and then we'll start doing some example equations, and then going through like explaining how we can make them easier using active low and active high, and then doing truth tables, voltage tables, working through Quartus, doing simulations, and then we'll actually show like a really good way to annotate circuits. So a lot of things that we saw with homework one was that some kids didn't really know like the best way to do it, and there was like some weird arrows and stuff. So we'll just show like an easy way to do it, and then we'll go through making the circuit because in lab one you have to make a circuit at the very end, and then we'll do questions. So these are all some QR codes. We'll leave them up for a little bit that you can scan. So they're videos that other people made that are going to be helpful with like doing mixed logic, switch LED, that kind of thing.
yeah. I guess we'll get started with a practice question, just getting introduced to mixed logic.
Okay, so this first equation, you can kind of see that right away it only has two inputs. So our goal is to be able to make this circuit using the simplest amount of gates possible and a way that gets the output. You all have seen this something like this before. Do you want to do this?
Sure. Okay. Um, Sorry, I need to adjust my pen settings real quick. Okay. Let's see. So the way that I would approach this is I'm gonna write this out with the actual like full names for these logic operators. So not A and not B, right? So I'm in parentheses. And first, I'm just going to find which logic gates are in the equation. So there's an AND here. So I'm just going to draw the symbol for an AND. I'm not going to draw like any bubbles at the input and output to indicate what kind of chip this is. I just know that there is going to be something shaped like this in the circuit. And so let me draw the inputs and outputs. There's only one logic gate, so not worried about that. The output is X. I'm putting empty parentheses to indicate that I don't know what activation level this is going to be yet. I just, I'm going to figure that out later so that I can optimize the equation. So I'll do the same for the inputs A and B. All right. So the first thing, I'm going to kind of do this inside out. So the first thing that I see here is we want to output not not and, right? That kind of sounds like a NAND chip, which also just happens to be like one of the chips that you physically have. So I'm going to figure out how to implement this with a NAND gate. So I'm going to put a bubble here, and I'm going to connect these two because there won't be any bubbles at the inputs. And just for clarity, I'm going to label this as part of a 7400 chip. And so if I want to output just, wait, sorry. If I want to output not whatever is input into here, like not A and not B. In order to do that, I need a mismatch. So a mismatch occurs when you have a bubble connected to active high, or when you don't have a bubble connected to active low. It's just a mismatch. And just for clarity's sake, I'm also going to draw the situations where you have a match, which is this would give you X and this would give you not X. You have a match when there's no bubble connected to X active high. You have a mismatch when there's no bubble connected to X active low. So in this case, I have a bubble. I want a mismatch, which means X has to be active low. And so I'm going to apply the same thing to the inputs. We want A as opposed to not A. and there's no bubble here, so an A active high. We want not B. I'm just going to draw the intermediate equations at the inputs. We want not B as opposed to B, and there's no bubble, which gives us this situation, which means we need B active low. And oh wait, what?
The output be high.
When that oh sorry. That one should be active high because there's a bubble there. Sorry.
No, it's okay. Okay, so this is like the easiest way to think of this. The easiest way to think of this like output here. A lot of kids that came to my office hours specifically were asking questions on the not and how to determine when you're doing an active high output or an active low output. So from this equation here, we can kind of see that like most people generally try to think of the output. Come in, come in. Trying to think of the output when they're making these circuits are usually always thinking of the output would be true, which means that it's active high. But an easy way to think to go from an X active high output to an X active low output, you only need an inverter gate, right? So a way to do this is you can remove the bubble. So here, I'm gonna erase this real quick so that you can just see. And then go here. So if we had the same inputs, so A active high, and then V active low, and then had our AND gate here. I guess that's a horrible AND gate. Uh, But if we draw a better AND gate like this, and then we have our inputs go into it, and then we have this output here, we would have A and B naught. But then this output here, if we did active low, like Daphne was saying earlier, this would be a mismatch, which would make the output equation exactly what we would want it to be. And that way you don't need the NAND gate. So those are two ways you can make a circuit, having different activation levels. And then also one thing is that if you wanted B to be high, you could just have a inverter gate here. So that's like, I think the basics of mixed logic. Do you want to move on to the next equation?
Yeah, I think we can move on. All right. So for this one, we're just going to go through a slightly more complicated example, similar to what you might see in your labs. Um, do you want to do this with just the like 74 row chips? Or
I chose activation levels for the voltage table, but here, do you want me to grab
I
it?
think
Okay.
I think it'd be better if those matched up.
Okay, so it would be A active high, if you want to write this down.
Okay, so we're gonna have set activation levels that we want to use for this equation in particular. So let me write these down. A active high,
B active low,
B active low,
C active low,
C active low,
and then X active high.
X active high. Okay, so I'm gonna start out kind of the same way as before, just placing the logic gates down and then adding whichever bubbles, in this case, not activation levels, but just the bubbles that we might need later. So I'm gonna start with an OR gate, so A or not B. A or B, sorry. A high, B active low. And second, we have another OR gate. This will be B active low, C active low. Let me make that a better OR gate. And then at the end, we are ANDing these two expressions together. And again, I always leave gaps for the bubbles at the beginning, at the output or input of these gates, because I might want to change them later. So finally, I'm going to write in X active high as the output. And let's see. So I'm going to kind of go from beginning to end here. So I want this equation, I want to output A and B. So if I want A, to be, if I want the truth value of A, um, let's see. I think it would be easiest if I don't have a bubble, or sorry, wait,
Does that make sense?
wait, why is there an AND gate there?
That's the point.
Oh,
Um,
okay.
right.
Um,
I mean, I'll see a better way.
do you want to take over for this
Yeah,
one?
okay.
Because I just didn't.
No, it's chill. Okay. So, where Daphne was going, so an easy way to think about this first equation, the A and B, or sorry, A or B, is we'll just go down the line, and so we see, okay, so we have A active high, we have B active low. Let's add an inverter. So you all learned in class that you can either use just an inverter like this, or you can write an inverter using a NAND gate. And so that's going to be important when we go to make this circuit later, because we only have NAND and NOR chips. So if I have a NAND gate like this, then that can work as an inverter, and we can have B active high or B true to go into this. And then we'll leave this empty and come back to it.
Can I add something real
Yeah,
quick?
go ahead.
So just to explain how the inverter works, can I explain like why this
Yeah, go ahead.
the reason that this works as an inverter using a NAND gate. So what you're doing is putting B active low into both sorry, let me get the eraser. You're putting B active low as both inputs into the NAND gate. So this will be not B and not B. And so let me explain this with the truth table. So this is what the truth table for um actually this is what the truth table is going to look like for the inputs and outputs of the NAND gate. So if this is, let's just call this C for now. So these inputs both have to be the same, right? So let's say that not B is 0, which would mean that B is 1. 0, NAND 0 is not 0 and 0. Not of 0 equals 1. So the output's 1. Then let's say that not B is 1. Not 1 and 1 is not 1 is equals 0. So effectively, if you connect one input to both inputs of an AND gate, it functions as an inverter. That's what I wanted to explain.
Yeah, I think Schwartz might have explained that, but Daphne did a really good job. I think that clears up a lot of confusion.
Yeah, so in that case, you would put like both, like here,
Oh
you would
yeah.
put two wires as an input into the.
I have a little shorthand of just adding it like just basically one wire. But if you wanted to like technically like write both of them, it would be like this. And then you have like two inputs, and then you have your NAND chip, and then it would go into the gate. Okay. So we have our B inverted, so we have A or B. Now, if we go down to the bottom, we can see, okay, we have B active low and C active low. So we can just use this like a normal NOR gate, or sorry, normal OR gate. Basically, we route them both in and we get OR. But now, because we're going to use this for our circuit, we can only really use 7400, 7400, and 7402, which is NAND and NOR, right? It's
Yes.
NOR, right?
Yeah,
Okay, that's what
that's
I
fine.
wrote a bad OR gate there. Okay, yeah, NAND and NOR. So if these are OR chips, we have to use NOR. So we go like this, and we go like this. So now we have these outputs are both knotted. But you can easily see that if we have, well, not easily, I guess, but a trick that you can learn in class is that you can invert the gates. So if we have I'm just going to erase some of this truth table over here.
No problem.
Uh, this so we just have more space. I don't know. Okay. Um, so yeah, if we have let's take for example a NAND gate, right? This is logically equivalent to a bore. So if we flip where the bubbles are and we flip the gate, you'll learn this is De Morgan's theorem later on, but these are logically equivalent. And the same thing with the OR gate. I don't know why I draw it like that. The same thing with the NOR gate is it's equivalent to a band. So this trick we can really use in this scenario because if we have these bubbles here and here from our NOR gate, we need a match, not a mismatch to go into here to get the output to be high, which means that we can use something like this, and then we'll get it like this. So we'll have X active high. Oh, why did I make that? So do you have anything to add? Did I make a mistake?
I don't have anything to add. It looks good.
Okay. So this is what our circuit should look like. And do you want to go into making a truth table?
Sure. So, I'm just going to cover a little bit more generally how to approach making a truth table for this. So, I guess I'll just go through this process and you guys can follow along. So, first, I want to write down all the variables we have. On the inputs, we only have three here, A, B, and C. And then I want to write the output on this side. Actually, let's see. I don't want to write the output just yet because I think it's easier if you write the intermediate steps the as you're doing each equation. So I'm just going to write out counting order, which is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. And I'll do the rest of them. So this might be a little bit of a tedious process, but please bear with me. So let's start with this term. I just kind of want to choose terms that you want to choose them in order that makes it um, easy to go step by step, I guess. So A and B is right in the front here, and it's a very simple operation to like transfer from here. So 0 or 0 is 0. 0, 0 is also 0. And then I'm just gonna go through wherever I see a 1 here, I'm just going to add a 1 to the table, and that is all of the rest of the rows. So I can just go through 1, 1, 1, 1, 1, 1. And that is 8 rows. Okay. And then when I see like a not term here, I think it's easiest for me to write the not term as its own column in this table. And so I'm literally just going to be looking at this column and inverting whatever it says. So 1, 1, 0, 0, 1, 1, 0, 0. And you can kind of use the pattern here. Like the first row in this table is going to change every four terms. First column. The second column is going to change every 2 rows, and the third one is going to change every row. So I'll also do this for C, and I just know that it changes every row except it starts at 1 this time. So I'm going to go 1, 0, 1, 0, 1, 0, 1, 0. Now I just need to do not B or C, which is very easy. Just put a 1 wherever I see a 1, which is 1, 1, 1, 0, 1, 1, 1, 0. Okay, and now the final thing is I just need to reference this row and this row for column, this column, because I need to end them together. And in this case, like, I'm not going to write out the whole equation. It's going to be x in the end, so I'm just going to write it as x. And so just so you can kind of follow along, I'll underline. But so this is an AND operation, so I'm looking for where both of them are 1. This has a 0, so it can't be it. This is a 0, so it can't be it. 0. Both of them are 1 here. 0 here. Both of them are 1. Both of them are 1, like, just so you can see where I am. Both of them are 1, and this one is 0. And we should have an actual truth table in the next slide, just to
If you click it,
if I click it, okay. Oops.
hit the X or something. Yeah.
Okay, there it is. So this does line up with what we had. So I guess now that we have, is there, I'm gonna, I would like to copy the truth table to the next slide. I don't know if you did it with that, but
I didn't.
no, you can just do however you want to.
001. Oh wait. Let me. What would be the easiest way to do this? Mm, right. 00101.
Because like I have a method, like the way I do it is I reference the truth table.
Yeah. I mean, that's how you have to do it that way. Um, do you want me to just like copy it on the laptop and then
Yeah.
move it over?
Or well, if you're on the slides, I'm on PowerPoint, so I don't know if you will be able to access my local file.
Um, are you fine with like losing the pen?
Um,
The, so,
I have drivers for it. I'm gonna stop sharing for just a second while I fix this, but it'll be back in like a second. Um, let's see.
does anyone have any questions so far?
Actually,
You might just be able to
we can
copy.
probably just use the like we can probably just write over the truth table side and like use that.
Oh, high key.
Yeah.
You want me to do the
Oh yeah.
voltage or do you want to do it?
You can do the voltage.
Okay.
I'll just I need to make sure I'm actually sharing. Ah,
Okay. Before we continue, like I said, does anyone have any questions? Speak now, forever hold your peace. Okay. All right. Okay. So, if you all, do I need to make it like pen?
I need to quit pen, yeah.
Well, oh, there we go. Okay. So the easiest way to do this is just looking at these. So we need to write out if it's active high or active low. So it's A active high, B active low, C active low, and then X active high. So the easiest way to do this is just straight up copying this table. And then I'm going to be a little bit lazy and just write it in this column, but we'll move it later. So when you have an active high signal, that means that when it's one, it's high. So we can just write an H here, H here, H here, H here, and then all the zeros will be low, 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 low. Okay. And then when you have an active, we can do the same thing for the X. So low, low, high, low, high, 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 low. And then for these active low signals, that means that they're true when it's low. So that would mean the zeros get H's, which is basically, I mean, it kind of makes sense because active low means true when low, so it's high when it's low. And we can just copy the same thing here. Okay. But now there's something that I need to point out. So this table is technically correct, right? We have all of our lows, our highs, etc. But the problem is that if we simulated this, it's not what's going to look like the output. Because remember, all outputs are in counting order. So, and if we're considering counting order to be starting at 0, 0, 0, 0, 0, 0, in voltages, this would be low, low, low. So in order to get the proper order for what our simulation is actually going to look like, we need to start with this. So we need to rearrange the table to be in counting order. So let me just erase this that I had here. And then, Okay, so our new order, we're gonna have uh, A active high, B active low, C active low, and then X active low. And I'm just going to start off by copying this row here with the arrow. So it would be low, 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 low. And then we're just going to keep going. So if I'm writing out the counting order in voltages, it's going to be low, 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 high, or low, low, high, then low, high, low, then low, high, high, then high, low, low, then high, low, high, 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 low, and lastly high, high, high. And then we could just go through each row and then just find the accompanying signals for these. So if I'm looking for low, low, high, that happens to be right above the arrow here. So if I look, the output is high, so it gets a high here. And we can just go through and do the same thing. So low, high, low, low, high, low is the one right above it, so it's low. Low, high, high is the first one, so it is low. High, low, low. High, low, low is the last one, so it gets a low. Then high, low, high gets a high. High, high, low gets a high. And then high, high, high gets a high. I kind of messed up here. That it goes like that. And then like that. Okay, so this is our true this is our voltage table, and this is in counting order. So when we simulate this on Quartus, the output should be in this order. Do you want to continue?
Yeah, so I think what we have after this is, I think that,
That should be right. I'm pretty sure. If not,
so,
there's something wrong.
okay, or
Oh,
there was one row I think that might need a correction.
low,
So
low.
low, low, high. Hmm.
I must have done something wrong in Excel when I made the answer.
Okay, well, let's say this one should be
This one should be
correct.
right.
Yes. So you're gonna see this one, you can just ignore it. Okay. The next thing I'm gonna do, could you pull up the circuit, like the picture of the drawn out circuit? Because I'm just gonna show like how everything gets implemented in Quartus. Like,
Oh, this?
yeah. Um, okay,
Yeah, here.
thank you. Just put there. Okay, this might take a second because I have to actually pull up Quartus and everything, but oh my, there's my mouse. Okay. This, it might be easiest if I do it all on one screen because this is like kind of hard for me to see.
Yeah, I feel like that should be a nightmare to do for this on the
Yeah,
second screen.
evil Quartus. Let's see. Actually, okay. Gonna share this whole screen. Oh, okay. Um, okay. So first, I'm gonna just gonna have to go through the process of like putting the gates in. So I'm just gonna do this quickly because we already um designed the circuit. Some more. So like everything I'm doing right now, we've already done. I'm just getting us back to the equation we made before, and hopefully this works properly. But I guess some tips while I'm at it. When you first draw a wire out like this and you see it's like highlighted in blue, if you start typing right now, like let's say I want to put in B, You can directly put in the label without having to like double click on it first. That's just something I found out when I was like newer to Quartus, I guess. And you'll notice I'm not putting in like underscore L. I'm not putting in I'm not putting in active high or active low just because I want to show you guys something with how Quartus handles its simulations in terms of it basically will ignore active high or active low. It purely deals with voltage, right? So this is B, this is C, and we have our output is X, and this should match wait, okay. Actually, wait, I do want to put active low here, but there's something specific I want to do. Some other tips for using Quartus. Um, do you have anything you know
Um,
about using Quartus?
I think that a little trick that I found was if you highlight a bunch of stuff and then I'm pressing the control key and then if I move and then release, I'm still holding the control key. So like if I just highlight everything, hold the control key down, move it, release my mouse click, and then release control, it'll just easily duplicate everything. Because I'm pretty sure that control C, control V doesn't work. Oh no, I guess it does. Maybe that just might be something that I couldn't get working, but the control key does work as well.
Okay, I didn't know that. So, okay, there's that. And I'm just let me put in the inputs. You should probably put repeat insert mode like me or unlike me just then. Okay, what I was trying to say is instead of putting underscore L in the inputs here, I'm just going to put like the actual values of A, B, and C. So what you'll see is that these correspond to the truth values of A, B, C, and X. Whereas I'm going to add something that should convert it from the voltage levels. So this is a trick that you'll probably use a lot in your lab. If you have a NOT gate here on the side, like completely disconnected from your circuit, if I'm going to put B here because we want to keep A as active high, right? So you can just have a completely separate NOT gate connecting the label of B to B underscore L. And so I'll do that again for the other active low inputs we have. C, we're going to convert it to C underscore low. And in this case, since we want to output X, well, sorry. Oh, sorry.
If you specified in simulation waveform.bwf, the inverse of it, would that also count as well?
What do you mean?
So in the waveform, you're able to use the self-counting function within the group, and then you can actually invert the one of the inputs, and then that leads to either active low or active high. Would that also
So you're
work?
talking about like if you wanted the output to be 101, for instance,
Right.
and you want the first bit to be inverted, you just put 001.
Uh, More of like, I think that's what you're trying to say.
So like an invert function on the actual waveform in the like when you specify it.
Yes. So instead of using knots in this circuit diagram, in the waveform, uh, let me think while I'm talking. Instead of using the knots, you invert the function and you specify that that's B low.
How
Um,
would you invert it though? Like in the group?
the only reason I would say first of all, you don't have to do this. Like you can just put be active low into the waveform itself. But the only reason that I would say you wouldn't want to actually invert like while you're like in the physical waveform, like if I'm just gonna try and pull it up so I can imagine. So you're saying like instead of if this
So
is be active low, instead of this, like actually inputting it as this.
Basically, but if you click on B
Yeah.
and then it highlights the entire thing, and
Mhm.
then if you click on invert,
Oh, yeah. Okay. So the only reason I would say it's probably best not to do that is because you want like you still want everything to be in voltage counting order. So,
okay,
and if you do this, um,
it's
it'll
not.
be out of order. Like you can see here it's going from like 001 to 110 to 111, but like you still, for the sake of your pies, like reading your annotated simulations, it would be better if you inverted it like either in Quartus or you just kept it as like you just need to keep it in counting order for the voltages.
Also, that can probably lead to some mistakes of you like not writing down which signals are active low. And then I'd say a lot of labs mistakes compound. So like just having one small issue might end up like adding 30, 45 minutes of correcting down the line. So I'd say bad practice, but I mean practice doesn't get you your grade. So like you can do it however you like.
Yeah, well, in this case, I think you would get points possibly taken off if just because like yeah, yeah. Well, like I guess if you did label this as be active low, then it would be counting up in terms of truth order, but you s-
I don't know.
I just wouldn't recommend
Yeah.
inverting it like that, is what I'm trying to say. But okay, let me kind of go back to this. So in this case, this logic gate right here is outputting the label x underscore low. And so this was kind of something that tripped me up, but you want to output x in the end, right? So the input into a logic gate has to be defined. In this case, it's defined as the output of this int20 band gate. So x active low needs to be going into the AND gate, and then you can output the label x. Because if you did it the other way around, like not x is, or sorry, yeah, not x is x active low, you would get undefined behavior. So you need to do it so that the defined thing goes into the logic gate. That's all I need to say. So this looks right so far, so I'm gonna compile it. And you do always want to use I don't know if you can see my mouse, but the analysis and synthesis compilation option, like you only need to do the full compilation if you are actually programming to your D10. That was something I didn't know.
Something
So
real quick is do not ever use the middle one.
yeah.
I was using the middle one on accident and it adds like a whole bunch of problems and it doesn't like it there's just don't use the middle. Either use the one on the full left or on the right.
Yeah. Yeah, definitely. You can use the left or the right one, but do not use the middle one under any circumstances. So, oh, okay. Sorry, I just saw some questions in chat. Okay. Sorry, this is a question on the voltage table that was worked out, but wouldn't X active low mean zeros would be H's and ones would be low?
Yeah.
Oh, wait.
But X is active high.
Oops.
Oh, that's just me.
Mm.
I drew it back. So sorry about that. So X is active high. I kind of had some bad handwriting right there. So this output's supposed to be active high. Oh, and then I wrote, oh, did I write active low? I must have written active low on the left-hand side, but X is supposed to be active high, which we can kind of see if we went back in the slides. We defined X as active high. So that is my mistake right there. Sorry about that.
Yeah. Okay. So back to Quartus, I guess. So now that I've compiled this, which you do need to do before making the simulation, I'm gonna let me get rid of what I have here just so I can thoroughly go through the process of making the simulation. So you guys have already probably seen this, but just for the sake of clarity, first you need to go to set end time. It'll be at like 1.0 microseconds. I set it to 1.2. Go to grid size. It'll be at like 10 nanoseconds when you start it, but you want to set it to 25 nanoseconds. So it should look something like this. And then I go to edit, insert, insert node or bus, node finder, list, and then you can use this button to copy everything over to this the selected nodes. When you hit OK, OK again, they'll all be here. Now I want to group the inputs together so that it'll be easier to see everything counting up. So I have my mouse on A. I'm going to shift click to C just to like group all of them together. Might have done that before. So group. Also be careful that you choose a name that isn't used by something in Quartus. So like if you use the term like input or something, that might cause errors. I don't remember this happening to myself, but I remember this being mentioned. So I'm going to call this like ins as a group name. And now you can see the actual value of what's in the input bus. So this one will count up and commit by 1. I always leave this at like the default settings. So now you can see everything has been populated, and let's run a functional simulation, see the changes, and this should all work, hopefully.
Yeah.
All right. And so,
Unless we did something wrong. I think
I think I need to pull up the truth table to check.
did we do something wrong with the circuit?
I might have done something wrong. This is ABC, so it should be high in only like 4 of these cases.
Interesting.
Can you pull up the circuit again?
Yeah, this should be similar, right?
Yeah.
B goes in, A goes in, band,
Is it a NOR?
nor. I mean,
Oh, wait, sorry. X is active.
but you inverted it.
X is active high in the end, though. Let me try this again, just to make sure. It does look correct overall. Oh, just gonna delete that. I guess this is also a debugging demo. So, I guess the first thing is checking that you actually have all of the activation levels correct. And then try simulating it again just to see how that changed everything. That is kind of weird.
Yeah, I just inverted it. There's
Like
only one.
it's like not the thing that seems weird to me is that it's not the correct number of like things being higher, things being low. Um like
Hilarious. So wasn't maybe there must be an issue. Maybe this should be a NOR gate because if we went back to our equation, it should be A or B. Okay.
oh yeah, I probably just misread it as
No, I think I might have drawn it wrong. I don't know where your Quartus went,
you I think
but I think I must have drawn it wrong. So if we look back, that should be a NOR gate.
yeah. Also, another, I guess, Quartus tip is when you delete a logic gate, it leaves all of the wires in the same place. So then if you replace it with one that's like the exact same size, you can just put it back there and it will reconnect to everything you had it connected to. So this should work. I think that was the issue. So I guess step 2 after making sure you have your activation levels right is that you making sure you actually copied over the correct gates.
Yeah. I say, at least for the earlier labs, a lot of your debugging is just making small mistakes. By the time you get past lab 3, lab 4, a lot of the mistakes will be larger things that are like, I don't know how to make this properly. So I guess just double and triple check, especially in your lab quiz, that you've written everything down correctly, that you have all of the symbols, all of the wires are connected. Sometimes you can have a little what you zoom in on Quartus and it's like one like box away from being connected.
Yeah. Yeah, something that could happen is I'm gonna zoom in a lot here and what might happen to you is you have a situation kind of like this where your wires are like really close to being connected. So it's pretty obvious in this case, but I've had it where it looks really, really close, and I thought they were connected, but my simulation wasn't like outputting anything, and I needed to like zoom in and see that they were in fact not connected. So you should verify that. If you see like circles, what was the mistake? The mistake in the Quartus simulation we had was I had like this gate here was I had it written as a NAND gate because I misread like
Okay,
the drawn out, or it might have been drawn wrong, but point is I accidentally put a NAND gate when it should be a NOR gate. So this actually, yeah, I think it would be helpful if I copied over the equation real quick. You can like copy paste directly into Quartus. That's another thing. So
all
we
right.
have this right above here, so you can reference it. For four inputs, the grid size should be 12.5 nanoseconds. I would I would keep it at 25 minimum because you have enough space to like you have plenty of space with 1.2 microseconds even if you have 25 nanoseconds for each thing. I can like create another input and just show you like this is just going to be a dummy input that isn't connected to anything, but I'll open up waveforms again. And to add something, oh wait,
Yeah, simulate.
I have to recompile it for another input to show up, but um, once that's done, I'll show you.
I would say leave when you guys learn about clocks later, leave your microseconds, leave your sim like all of the like the 25 and the 1.2 and the default clock that you'll learn. Just leave that what it is until the later labs in which you're having like lots of data because usually you'll never end up using the whole thing.
Yeah, I think there was exactly like one time in the entire like in all of digital logic that I actually like made like that I extended out the time. And you can just extend out the time. Like you can make it end at like 2 microseconds or 3 microseconds. I wouldn't recommend making the interval smaller just because like it's
So
yeah, there's no point and it might lead to more errors than just like keeping it at a slightly larger value that it can actually handle simulating. So grouping, you can right click to ungroup things. So I want to make a new group. I'm going to call it the same thing. You can also just like if you set count value to something that already has values in it, it'll just overwrite everything, so you don't have to worry about that. So like if I zoom into this a little bit more so you guys can see, let's see. So I hit 1111 400 nanoseconds in. So if you're for these early labs, you just need to simulate going through every single value. If you hit 1111, that means that you have covered every possible case. You don't need to worry about running it for longer, annotating for longer. Like you have covered literally every combination of voltages that there are. And when you get to having more inputs than four, the thing is you won't want to annotate every single one anyway. Like you're going to not be showing every single case. You're actually going to be ordering your inputs in a way that is logical. Like let's say you're trying to show an adding function. It makes more sense if you have like one test case of adding like two numbers together instead of like having them in non-logical order. I guess I hope that makes sense. But the point is don't change your simulation values unless you want to like extend it to longer because you're not hitting every case. That's all I have to say. So anyway, after all of that, let me run the simu actually let me undo all of these things. You can just oops, accidentally deleted the whole group, but that's fine. I'm not using D. It's literally going to do nothing, so group these together. I'm not going too fast, but I already covered this. And you can also drag tree order things, so you can see and count. And finally, I'm going to run the simulation. Okay, this looks great.
I should be
So, and then I want to pull up the truth table to compare to this, because that was what I was doing. Um, Ah, okay. So I need to think through this. So let's just quickly verify that this matches our truth table, right? So what I like to do is I look at the X column here. I see which one has fewer, like out of 0 or 1, are there fewer zeros or fewer ones in the table? And it kind of looks like there are fewer ones, so I'm just going to check if the ones are correct. So there's a 1 at 0, 1, 0, which is right. There is a 1 at 1, 0, 0, and then for two more after that, it is high, which seems correct. And that 1, 1, 1 is 0. So that's the process of how I quickly verify that this matches the truth table. And so you might notice that this is different from our voltage table that we made, which, shoot, I don't think it kept the annotations for what the voltage table was. But I mean, you guys can remember it was like slightly different, right? So
It should be the same because we reoriented it in counting order.
what I mean is, so how do I say this? So because in order to make B active low, I inverted the value of B. That means that the values of like 0, 0, 0, 0, 0, 1 here you see are actual truth values. But if I take out these knots and I rename everything back to being active low as it was, and I recompile, what you're gonna see is that the output is going to match the voltage table instead of the truth table. So right now you can think of these as 0, 0, 0s, but if you don't have the inverter, then you should think of these as low, 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 high. I hope that makes sense. But let's see if this compiled properly. Okay. So now I'm going to do a new simulation. And by the way, and this is just a side note, in the project navigator, it'll by default have you look at, like, this dropdown will be set to hierarchy. But if you set it to files, then you'll be able to access your waveform simulation like directly from a file explorer. That's just something I had to learn. So let's have these side by side. On the right is what the truth table looks like, and on the left is how our voltage simulation is going to look.
Might give you
Oh.
because you need to find B active low and C active.
Oh yeah, okay. I do have to remake these. I just have to go through this whole thing. That should be good. And now I'm going to run a functional simulation of how the logic works. So,
That should be, I remember there is low high. So this should be equivalent, this side on the left should be equivalent to the voltage table that we made earlier. And the thing the simulation on the right should be the truth table. So what we can see is that when we give these all activation levels and we reorder them, that it's going to actually be in a different order. However, we're going to still have the same number of truths. So we have one high, or well, we have four total highs, and then we have four total highs over here. It's just in a different order because we need to reorient everything because of the active low, active high. But we saw that when we went over the voltage table earlier.
yeah. So I guess the ultimate reason that I'm showing you guys this demonstration is because I think in lab part 1C or lab part 1D, it'll have it's like the thing where you need to combine two different circuits that use that use a certain variable, which I think is B with different activation levels, right? And so it'll have you invert one of them. It'll have you invert, I believe, B in order to get B active low. And um if you The thing is, by doing that, you make the behavior match the truth table instead of necessarily like the voltage going into that variable B. So this is, I just wanted to show you guys how Quartus would handle like using truth values as inputs versus voltage as inputs. That's kind of all I had for the Quartus demo. Was there anything you wanted to add?
Just a little bit about Quartus. So is this already post simulation?
This is post simulation. There,
Do we
there's
have,
so many things
okay.
open.
We have one that's open here. Okay. I'd say a little tip is if you double click in the left side, you can instantly open the node finder. That way you don't have to do file edit insert every time.
Oh, sure.
And then also, I don't know, I can't really remember the early labs, but I do remember that sometimes you have multiple BDFs in one file. An easy way in hierarchy, I don't know if you guys are going to remember this, but if you have a BDF and I'm currently in it, like I'm just clicked in it, if I do Control Shift J, it's going to create that as the top level entity. If I make a new BDF, new block diagram. If I make a new block diagram, block two, do Control Shift J. Why is it not?
I can also full screen this.
Save it as a file.
Oh, do I?
Oh yeah, I think if you add like a text thing to it or something, I think that'll register it as like
Oh, okay.
being a new file or literally anything.
New file. Oh, there we go. So we save it. Block two. Then Control Shift J. You can see on the left that it's changed from all A's to block two. And that's just an easy way that like you can move around easily without having to change hierarchy and go here and set as top level entity, etc., which I think is kind of a cool trick.
Yeah. And just general guidelines, make sure every single file you have in your Quartus directory doesn't start with a number. Make sure that you don't have any spaces. Just make sure you're not using reserved words. Like I try to be very like careful about this. Like I wouldn't call something like input.bdf because there are other things in Quartus called input, for example. Like just try to avoid a word that you would like see in Quartus.
Oh, and if you ever get an issue with, it'll say something about inst, it might be because these names. So it'll just give you a random error and it'll say object is already defined, and you'll notice like this might be like named inst19, and they'll have the same name. So you just have to name it something different. Like you could just name it like Norgate.
Yeah.
Just literally anything else, and it won't give you a compilation error.
Yeah. Yeah, it doesn't this is the only time that like the inst names underneath here actually matter. Oh, okay. And there's one more thing I wanted to go over real quick. So, part of the lab is you will need to add pin numbers and chip names into your wiring diagram of Quartus. And I'm just going to show you guys how to do that. So, you'll need to refer to the pinouts for the 7400 and the 7402 chips in order to do this. But let's assume you've already looked at them and you've already chosen the pins you want to do. So I'm going to use this NAND gate as an example because NAND is on the 7400 chip, right? So right above it, I'm going to put 7400. If there were more, if I needed to use more than one chip, I would specify like 7401A or something, but we're assuming we don't have any of that right now. And so the first three pins on the 7400, 1 and 2 will be inputs to the NAND gate, and 3 will be an output of the NAND gate. So above the first wire, I put a 1. Above the second wire, or honestly just like near it, put a 2. And then at the output, I'll put a 3. And to be honest, it is probably better to work these out possibly on paper first because what you'll see when you wire it up, when you wire what you have to do for your lab, it'll probably end up being like a complete mess of wires if you literally just go like click like selecting the first NAND gate as your first input. Like what I'm saying is you should try to choose your pin inputs and outputs in a way that will make it easy to physically wire on the board and easy to debug. So the less things you have crossing over from one side to another, because you have 1 through 7 on the left side, you have 14 through 8 on the right side. The less things you have crossing over, the better. The less things you have like jumping over other pins, the better. Just you'll need to like you can't just figure this out by sitting down and looking at the pins. Like you need to experiment with it yourself. But I think that you should just work it out, possibly do it on paper so you can erase easily, and then put everything into Quartus. But once you have that, um, I think I don't remember exactly what it was for NOR gates. I think it's like 5 and 6.
It's a reverse, so it would be 2 and 3 are the inputs, and then 1 is the output.
Or yeah, okay. So let's just do it again for another gate because you need to write both the inputs and outputs for each chip. So this is what it would look like for NOR gate. I'm gonna write 74 too. And like it's a little bit messy. As long as you can tell like which which thing is where, it should be okay. And that's all you really have to do for wiring diagrams, if I remember.
For this lab and this lab only, he's going to ask you to make a little diagram on like, I think it's in PowerPoint with a little breadboard, and you have to draw your chips and your wires. That may be that may seem tough at first, but I would say honestly, probably try and draw out what the pin numbers are going to be on paper, make it in Quartus, make it IRL or well on your breadboard and then go back and draw on the PowerPoint because it may be a little bit hard to see at first. I mean, everyone should have made a circuit in Lab 0, but it may be hard to see on the PowerPoint how it's like going to be properly structured with the chips and the resistors and the LEDs and stuff.
Yeah. Yeah, I think that's a good idea. And once you build it too, it'll make more sense like what you have to put on the like on the PowerPoint drawing of it. I guess does anyone have any questions before we move on? Okay, yeah, I sent the printouts in chat. Are you guys good?
I have one question. So like, this is more to do with like simulations, like working in the lab itself.
Hmm.
So at one point, like I know the difference between timing simulation and functional simulation, but at one point he references a simulation timing diagram.
Hmm.
Is that a functional simulation? Or what is a simulation timing diagram?
I would assume it's functional.
Yeah, I think it's a functional simulation. It's just saying that like the simulation, it's giving you data over time.
Okay, yeah, that was just
Yeah.
Unless he specifically states timing diagram. He's going to say like max 5 time. You actually never use it other than lab 1.
Okay.
Yeah.
And on that first homework, I think.
Yeah.
And at the end of question 5, it says to define the the switch block and then the light block on the circuit diagram, I think.
Mhm.
Is that on the Quartus or is that on the paper?
So he gives you, can we open the website?
Yeah. Um, I should probably.
Is the way that it was worded, the word like the name was the same as circuit diagram, which is on the Quartus.
I think it should be in your Word document.
Okay.
It'll be like you paste a picture of it like from the PowerPoint template, put it in your Word document, and then underneath put like figure whatever it is.
So
Switch diagram.
that's using these. So it's asking for, so basically like the true position of the switches. So if you have an active low symbol, you can kind of see already. If it's active low, that means this little black box is up. And if it's active high, the black box is down. And then for the LEDs, you can't really label if an LED is active high or active low. So you just say what LEDs you use. So if I'm using these LEDs in my lab, then you put them there. And it should match. I mean, there's no real, I mean, we could probably check it in your lab, like with your demo, but I'd say just try to have them match which switches you use and what LEDs you use.
Yeah.
Okay, so this is not going to be put on the Quartus.
No,
No,
I don't think you can.
You take a screenshot of this and then put it at the bottom.
Of the Quartus screenshot?
No, you take a screenshot of like this block after you're done editing it, and then you put that wherever it asks in the PDF.
Yeah. Yeah. All right.
Do you want to do annotation or physical first? I think we have annotation next.
Yeah, I think Yeah, we did simulation, so we're gonna walk through the process of annotating simulations, either with like an iPad or some pen having device, or with the method that I think he has with using Word or Excel. Um, I think it would I think we should do the iPad one first because you'll probably want to do it on your computer. So I'll be quite honest. The quote unquote method that I have for annotating things with a pen is kind of messy, but I think if you just follow some general guidelines, you'll essentially what you're trying to do is you're presenting a simulation to your Pi. But the Pi has no idea what all these lines mean. You've been looking at it for a while, so you might kind of get what's going on, but your Pi just sees this diagram and you are trying to explain to them that not only how it works, but that it works correctly. So you're trying to demonstrate that your simulation is correct. And there are few different things that you should do to accomplish this goal. You should reference either the voltage table or the truth table. You might want to reference both of them. You should, you might want to write in sentences. What I always did was I would write in small explanations underneath something that I highlighted to like explain logically why something worked. And you also probably want to use like basic annotation strategies like color coding, using layers in your program if that's possible for you. Um, Generally just try not to be too messy with it, try to make it as readable as possible. So I'm just going to open up my one of these simulations that I made. Not that one because it is wrong. Um,
Oh.
so yeah, this one, I believe this one was the voltage
Yeah, it should
simulation,
be.
right? Yeah, so this is good because you're going to be annotating the voltage simulation, probably not the truth table simulation. So the process that I'm going to do, I'm on a computer, so this might be different if you want to do this on a tablet. Specifically, I have a drawing tablet that connects to my computer, which not all of you might have. If you have something like this, then you can follow my workflow. If you don't, you can just open it up in whichever image editing program you'd like to. I would personally recommend something that supports using layers, because I think that will make it easier for you. Honestly, as long as you can edit the image without losing data from below where you write, it should be okay. But anyway, I'm going to take a screenshot. I will only take the screenshot up to where the last thing I need to annotate is. So once I hit 111, I've covered all the possibilities, right? And I like to leave some space below so that I can write in things. I don't want to leave too much space because otherwise like the image dimensions will be all weird when I paste it into my program. But I'm gonna take something like this, like almost 43. I'm gonna open up in Paint. So Microsoft Paint does have layers now. You might be comfortable using a more complicated drawings program. I don't think you need anything too complicated. But as you can see on the side here, I can make layers. I'm using a pen, so hi. Okay, and let's see. So I think it's really helpful if you can paste your voltage table into your image with the simulation. You might not need to all the time if it's depending on what you're annotating, but for this lab in particular, I will say you should probably paste your voltage table in. And I think there was an error with the one we had, so I'm just going to write it in for now. But imagine that this is, and I'm just going to be copying from here, but obviously don't do this if you're not completely sure if your Quartus simulation is correct, right? Because honestly, when you annotate this simulation, you should be proving to yourself that it works. Because this is how I found my errors a lot of the time, was going one by one, checking every single case. And when I found an error in my simulation, I would stop annotating and redo it, which is maybe not the most efficient way, but that's something you can do. So, and then let's just assume this is in counting order. So I'm gonna write in 000. Actually, no. L high, but please assume that it's just going up from low, high, low after this because it is a lot of writing to do all that. So 0, or sorry, L, H, L, 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 H, H, H. Um, so your annotations don't need to be super complicated. Um,
Just say like these are high, these are max terms, min terms.
yeah, so you can say like you could literally draw an arrow from here to here, like, and then you might even want to write in X is high when maybe don't write this for every single term, but if you feel like this makes it easier to like justify it to yourself, you can totally write something like this in. And then you might want to group together some of these. So I'm going to group together these three at the end, and I'm going to draw an arrow to them. So like you can see that these three from 101 to 111 is high. And I think if you did something like this, you showed where it's high and you just omit writing an arrow or something when it's low, I think that this should be sufficient to justify that your simulation works and it matches your voltage table. So I guess if you wanted to move on to
Okay.
if anyone has any questions, but I think we can move on to another method to do it, which is using Word or Excel if you don't have like some device with a pen on it.
Do you have Word and Excel?
Um, I do. I guess we can just do it on mine.
Well, I mean, like, I don't have the simulation screenshot. It's like
Oh, okay,
all that I
yeah.
was thinking.
Yeah. Okay. It's just I have so many things on my screen right now. It's kind of overwhelming, but okay. You can just
Okay.
honestly just open.
All right, so this is my method because I
Wait,
don't.
sorry. Stop sharing real quick, just in case.
Oh, true.
I don't know if I had something open that,
Shouldn't have been open.
yeah.
Or like answers or something.
Yeah, I'm gonna, mm, let me just unplug this for a second. But you guys don't see something you're not supposed to. See, like, I think okay, it was fine, but I can open a blank Word document and a blank Excel sheet for you.
Yeah.
Okay.
And
So that like see the person is.
oh yeah.
Yeah. Uh, yeah, my PS2 emulator is only for playing Horses 2. Okay. Now let me share my screen.
Okay. Good catch. Sorry about that.
No problem. It's not gonna play what that is it?
What do you mean?
Or,
Okay. So if right away we can copy our simulation into Word, and then we can go to Excel. And so we're just going to add in our table. So uh A, B, C, and then X. So I'm pretty sure it was 0, 1, 0, 0, 1, 1, 1,
yeah.
0,
Yeah.
right? Okay. And then we can do our 0, 0, 0, 0, 0, 1, etc. through 1, 1, 1. Actually, I'll just go through it just because uh, this should be 1, 0, 0, 0, 0, 1, 0, and then 0, 0, 1. Okay. So if we have our if we have this in Excel, we can obviously use the formatting that Schwartz kind of wants us to do. So we make a little title, and then we have some borders, and then we mark these with gray. So this is kind of the way that he wants us to do it. And so my way of annotating is I'm actually going to take this gray off, and I'm going to go row by row and color it using like red, green, blue. So red, orange, Let's see if I run out of colors. Green, dark green, blue, dark blue, and then purple. Perfect. So now that we have this, we have our truth table and it's been kind of annotated. And we can take a little screenshot and bring this into Word. And I'm gonna just go ahead and crop this to be a little bit smaller. And so now we can just do the rest of our annotation in Word. So now that we got this truth table, we need to correctly correspond this with it. So a trick that you can use is if I insert a shape and a square, and I'm just going to go along right here for the 000 column and make a square over it. I can change the outline to have no outline and the fill to be red. Now, the fill is a little bit dark and you can't really see through it. So if I go to fill and then more fill colors here at the bottom, it'll have selected our current red, and I can change the transparency to like 30%. And you can actually see through it. Now we should probably have transparency a little bit higher, probably closer to 60. Yeah, there we go. So now this column basically has red masked over it. And we can duplicate this for all of the other columns. And I actually won't go through all of them, but then you can just change the shape fill here. And after copying, it'll keep the transparency. So red, orange, yellow, etc. And then I could just go down here and say color matches for columns slash rows. And if let's say there's something in particular, so in your later labs, you'll notice like, okay, let's hyper focus in on this one output. For some, like it might be like this output means something. You can say red designates output one or something like that. So basically how this works is so you can drag and drop text boxes or just boxes in general that can be of certain values. So like you can say that this is important or this is important while leaving behind it your simulation so your Pi can see. And then you can color code your truth table using Excel, which is just my way of doing it because I don't have an iPad and I don't want to draw it out on paper and then color it. So
Yeah, I mean, either way of either way of annotation works. I think something to note here is like whether you're doing it with an iPad or on Word, I think that writing things out, even writing things outside of your annotations, like right below it on the image, if you can if you can explain it better in words than in drawing something, I think even that, the goal is literally just to show that your simulation works. So if you want to do that in words, if you want to do that with a bunch of arrows, if you want to do that by color coding, anything works. Just like be able to logically prove it in your head. Um, that's all I can really think of
for annotating.
for annotations. Yeah.
Did you write something down in the slide?
Did I? I think I kind of went over what was on the slides. Like I just went over some guidelines for it. So I think
Do you want
then
to do physical circuit then?
yeah, I think that's what we have next.
Okay.
I will stop sharing my screen for now. Did anyone have any questions? Because we're just gonna get the circuits set up. Right?
You have a free USB port.
I can get rid of my tablet.
Okay. So I made this circuit with it was technically wrong as we determined that I made this with like the NAND gate at the top when it was supposed to be a NOR, so the outputs won't necessarily match, but it's pretty much the exact same thing that you would see. Okay. So basically what we have here is I'm gonna do my best to try and show it. We like be big. Uh, and perfect. Okay. So I'm going to do my best to try and show it. So right here, you can see I have my switches, right? Switches are off when they are down and they're off when they're up and they're true when they're down. So you can kind of see there that switch right now is off because it's up, and then the rest of the switches are on because they're down. And so right here I have my NOR chip, I believe. Let me check. It's an OO chip, so that should be NAND. And then I have my O2 chip here, which should be NOR. And so what you should take into account is you obviously need your power and you need your ground, which are down here. And these rails, if you don't know how a breadboard works, the power will go, these will go across, and then everything in the middle will go down, and you should have your chips in the middle. I have my resistor SIP pack, which basically is single inline package. So it's just a line and it has a little voltage. Be very familiar. It has a little dot on this side. You will get very familiar with the dot because the one time that you do it the wrong way, it's not going to work. And then, so I have all my circuits. So like Daphne was saying, you can kind of see right here that I have some wires that are lying flat on the board and then some that are jumping. Try to make as many wires as flat as you can. I challenge you guys to try and make some circuits with all flat wires. But down the line, in your later labs, there's going to be tons of wires, especially lab 3. You're gonna have tons of wires, and if you try to do them all flat, the lab will not work because of what you'll learn later, race conditions. So basically, you just have your logic. So I use the pinouts, and like we said before, the pins. So my inputs from my switches, which are grounded, because remember we do pull up resistors and then we ground the switches. So I have my inputs from my switches, and they just go straight to the gates with the pins. You can kind of see, I'm not going to walk through how like all the pin diagrams because you all made circuits in lab 0. But basically you just use the pinout diagrams and you recreate the circuit using these switches. I would also say as a little tip, always have these notches pointing left. So this board is reversed, so when I'm actually looking at it, these will be pointing left. And general rule of thumb, having them point left is going to make it a lot easier to debug if it doesn't work. So I do a lot of logic in here, which you can kind of see. And then I have this green wire here, which is my output. Always have your output wire go through a resistor. So this is a resistor dip package before going to your LED, as we all kind of learned that if you don't have a resistor, it goes boom, as Schwartz likes to say. So you have your resistor and then you go to your LED. And then if I make it have an output that's high, uh, like this, it'll go on and you can kind of see that it's on. Another thing is, so the LED has, you can kind of see here, it has some writing on one side, and then it doesn't have writing on the other side. So the writing is actually the positive end.
The writing is the cathode, yeah.
Writing is the cathode. So this is
Sorry, no. Writing is the anode.
writing is the anode. And not writing is the cathode. But the writing end is positive. So if I'm making an active high signal, I route the active high signal to the writing, and then the not writing goes to ground. So you see this end is empty, and then this little yellow wire right here goes to ground. So that's how the LED works. And so if you're wondering, back to your question on the active high and active low LEDs, so this LED right here, I would draw with an active high signal. And then if we look down here, these switches, so this switch is up. Let's say this is the true position, right? Like defaulted up. That would mean that this would be active low, this would be active high, and then the third switch would be active high, because it's in the up down up orientation. And that's about it for physical circuit. I'll have this on the table if you guys want to look at it, but does anyone from online have any questions about the circuit?
I guess the way that I remember which side is the anode versus cathode is cats can't read. So the side without any writing is a cathode.
Oh, that's true.
And I also think of it like
Cats are bad.
yeah. But the other like you know how there's like a triangle with a line under it? Like triangle line under it, and that represents the diode. The side with the line is the cathode, and it kind of resembles like a cat's pupils, like the slit pupils.
Mm-hmm.
That's how I think of it. But yeah, I don't think I have anything else to say about the circuit itself.
You're only building one circuit for the at the end with part 5. So everything else is with Quartus or drawn.
Yeah. Yeah, and just to make it clear, you're able to bring your built breadboard to the lab demo. Like you don't have to rebuild it while you're there, but you do have to make sure you're not looking at it or anything during your lab quiz, because that's the point of having a small breadboard in your kit.
And then another thing is we always use 3.3 volts. So I don't know if you can kind of see, but the breakout pin from the DE10 has 5 volts and 3.3 volts. And if you use the 5 volts, it'll probably break something. So please make sure to use 3.3 volts.
Yeah, and Davis kind of mentioned this, but be very careful with the orientation of, I'm just gonna pull this up. Like, be very careful with the orientation of your NAND and NOR gates relative to the U. So I always imagine the little part with the U on top, or as being the part on top. Relative to that, the bottom left is where you connect ground, and the top right is where you connect VCC. So they're on opposite, like they're as far apart as possible for a reason. And if you connect them like quote unquote upside down or in opposite directions, it will heat up and be very hot. And it burned my finger when I was touching it when it was like that. And overall, it might not break your part. It'll be bad for your finger and for the longevity of your part. So just don't do that. Um, and if
Surprisingly,
sorry.
sorry to cut you off. Surprisingly, these parts can withstand a lot of mistakes. I've accidentally written ground to power, forgotten a resistor or something, and they've semi-worked. I mean, don't intentionally try to do it, but when you notice your mistake, you're not gonna have to like buy a whole new chip.
Yeah. I would say like the top few things that have gone wrong with me for like in circuits are forgetting to connect the switches to ground, forgetting to connect the 74XX chips to power or ground. And sometimes I would just mix up like LED anode versus cathode in my head. And when I flipped it backwards, it would work. I wouldn't recommend doing that as like generally because it's probably bad to have it going in the wrong direction, but
Well, I mean, if you just have it in that wrong direction, it's just gonna be active low.
or well, if it's in the wrong direction though, it should be connected to like the
Oh,
opposite like VCC or
yeah,
ground.
sure.
But, like as a last resort, like if you think you might have forgotten which one is the anode and which side is the cathode, I think you can just flip it around. It should be fine. Like try it. You should probably reference like the hardware diagram. Like just try doing active low versus active high. Like maybe you were wiring it wrong by habit, but those are the things that I think for me, I got them wrong a lot. Was there anything you had in mind like when you were doing your circuits?
A lot of times the hardest part for me getting started with Lab 1 was realizing, like I said before, the side with on means off, which I guess is like counterintuitive.
Yeah. Yeah, that like if you feel like I thought that my entire like I thought that I had somehow switched the inputs. Like I thought everything was literally backwards. It was actually working as intended. I just thought that active high was active low and vice versa. So yeah.
I think
Um
that's all that we had planned. Do you guys have any questions?
yeah. If there's anything specific on your lab, if there are no more questions from the Zoom, we might end the Zoom meeting, but if anyone has like specific questions, please feel free to ask. Um
Have you guys started Lab?
Lab one?
Mhm.
Yes.
No, definitely not. No.
Definitely not in my lab section, it's tomorrow.
Oh,
No.
there's a lot of people more people than you expect that start their lab day before, day of.
Yeah, yeah, that was me. I got them all turned in somehow.
Oh, I do have a question about the formatting of the document itself. So the lab document is very wordy with all like the parts. Do we have to copy like the exact exercises onto the document? Like
copy
word
the
for word,
questions.
copy the questions word for word?
So, my pi, Landon, you'll probably see him. He's made a couple of videos. He told our lab section that he didn't really care and he just cares about um the screenshots. I told my lab the same thing, but I think that would be pi dependent because they're grading your work. I don't think you're gonna need all the full questions because the pre-labs are more like, did you walk through it and actually do it? So
Like, I think if you cut out some of the bulk of like those giant like explanations in the questions, like if it's clear to you which question it's referring to, and you think it would be clear to someone who has like looked at the lab a lot, I think it's fine.
also it's like you have a caption on every image.
Mhm.
So if you just use the caption saying like voltage table for question one, part one, then you don't really need to write the question.
Yeah.
But I would say for homeworks, do include the full question.
S Someone asked, can I ask about the way I format the pre-lab? Um, yeah, what was your question? So you were asking, so you put the screenshots with like the truth table and voltage tables and like in the pre-lab exercises part, and
Yes.
so whether you need to put them again in the requirements part.
Yes.
Um, I would say that they're normally like voltage tables and truth tables and stuff normally would only go in the requirements section actually. Like I'm not sure if it was like a specific
Is she talking about the like the section at the end?
yeah, like the pre-lab requirements, I think.
It's all like pre-lab question. Like if I think the section is like it's the first page and then it's like pre-lab questions and then there's pre-lab requirements. You can just delete the pre-lab requirements with like all the text at the bottom.
You would put that in the requirements because the questions are or exercises are more like it'll ask you a question that you answer like like in words like um maybe an answer to a problem or something. But if it's the normal requirements of like have like your circuit, the pictures of your circuit or diagrams, like truth tables and stuff, I would say that those generally go in the pre-lab requirements section. And ultimately, like I think as long as it's clear to your Pi that you have all of the things, like all the exercises, all the requirements in the document, it'll be okay.
Oh, okay.
Especially for the first lab, like if your Pi has an issue with it, I think they'll explain it to you and you should be okay.
Yeah.
Okay, thank you.
Yes. Does anyone else have any questions? Yeah, no problem. Um,
I think that's it.
yeah, well, feel free to post messages in help channel or message one of us if you have any more questions. Yes, bye
Good
bye.
luck.
Good luck.